gravitational potential energy. So assume you have one star, let's say star A, and you have another star B. Their distance between them is r. And if we choose A as the orange of the coordinate and use this direction as the increment of r. So according to Newton's law, the gravitational force between these two should equal to F equal to G m r squared. M is mass of the two stars. So from this you can see if r equal to infinity, then F equals to 0. Means when two stars are very far away, they do not have gravitational force between them, and they are free to move in their own way. Now the question is, if my star B is not originally at the distance r away from star A, rather it is very far away, let's say infinite distance away from star A. So it's free from each other, there's no interaction force, so there's no kind of combined potential energy between these two. Now the question is, if we try to move this little m all the way to original position r, how much work I need to do in order to get that done? So you know, this little mass and the big mass, they have attractive force due to Newton's law. So they tend to attract each other. If I move the little mass a little bit closer to the bigger star, their force between them becomes stronger and stronger. So if I don't hold it up, it will accelerate and eventually bump into each other. So my question is, how can we move this star B or little m all the way to r distance away, and without those two actually accelerating and bumping into the other? All you need to do, or all I have to do, is I will apply additional force on the little star m here and try to cancel out attractive force between those two masses, so that the net force during the movement on the little m is always 0. This little m here, and it got attractive force by big M, and this is the force I'm going to apply, okay, to cancel out at each position. Okay, this is the position, for example, this is the position R. R is measured from this original point. So at this point, my force is always equal to the attractive force. So the little m will not accelerate. So it can be moved adiabatically to the position we want it to be without crashing to the big star. So for each small step, when I try to move it, I can hold this force constantly to counterbalance the attractive force over that distance. That distance we can call the ds. So now what work I need to do in order to hold the small star? So the work I need to do, me, should equal to what? My force. The force I have to apply and the force at the section is section I. Let's say section I. This is the force I'm applied, and this is the force, this is distance in the direction of my force. And for each segment, I have to add this up together. That will be the total force, total work I have to apply to the little star in order to hold it and move it slowly to the position. This can be written in different way. We know the force I need to apply should equal to the Newton's gravitational force, which in this case is Gmm over r squared. And the direction of my force is try to pull the little force away. And so the direction of my force actually is along the increment of r. So it's in that direction of r. Because attractive force we tend to put in, I have to put outwards. Outwards is in the direction of r. So the ds in this case effectively is dr, and they're in the same direction. dr is going to the right, and ds also going to the right, and my force also going to the right. Remember, the attractive force actually going to the left. Okay. So if that case, this is a classical integration problem. You divided the path into so many tiny little segments. Each segment have constant force, and the segment distance is very small. Then this can be an integration of a G m over r squared dr. And where do we start? We start from infinity. Where do we end up with? We end up distance r. So this can be written into, if we do the integration, should equal to G n m r. And you have to evaluate this from infinity to r. So this equals to minus G m over r. So this is the work I have to do in order to hold up the little star, do not let it accelerate or crash into a big star. Okay? If that's the work I have done, that means what is the potential energy that the little star have gained from me? So the potential energy that little star has gained should equal to the work I have done to it. And in this particular case is G m over r. It's interesting that in this case the potential energy is negative. And so where is the potential energy? Zero. So when r equal to infinity, potential energy at this position equals to zero. That means when the little star is very far away from big star, its potential energy formed within the big star is zero. Means they don't have influence against each other. They can move any way they wanted. Okay? But when they come in a little bit closer, they will have a potential energy which is negative. That means the little star move in to a position that it has to give up energy. Okay, give out energy to the system, and these two stars now start binding and become a more stable system, staying together. Okay, that's the meaning of negative potential energy. Okay, so when you have multiple stars in the, for example, you have 1, 2, 3 stars. This is a big M, this is a small M1, this is M2. When you put those 3 together in this way, then you can calculate, for example, this is R1, this is R2, this is R1, 2. So what is the total potential energy of those 3 star systems? Originally, all 3 are very far away from each other. Each one have potential energy 0. They don't interact with each other. When you put those 3 together, what's the total potential energy of the system? Well, since Newton's law is individually applied, means each star will have attraction with another star. And they all follow Newton's law, and everything else will be added up together. Force is added up together as a vector. Energy will be added up together as a scalar, because energy is not a vector. In this particular case, the potential energy of the total system should equal to potential energy between, for example, this is a star A, star B, star C. Should be between star A and B, and star A and C, and don't forget the star B and C. So in this case, we can say A and B, according to previous formula, the potential energy is G M1 over R1. So put A to C, then the potential energy G M2 R2. And what about between star B and C? Okay, the potential energy is G M1 M2 and R1 2. So this is the total potential energy of the 3-star system. Thank you for watching.